Okay, we're back at it for part two here. We were just talking about if two vectors are not parallel in the plane, that means that any other vector can be written as a linear combination of them. And we were talking about that briefly. But there's what we're talking about in algebraic terms. If I took any old W that I could think of that's in the same plane as U and V, then I'm going to be able to find values of K and L so that a multiple of U plus a multiple of V gives me this magical vector W that I'm after. Okay? And we're going to actually show that using a specific example back on your page. So we're back on your page. Your page is flat on your table there, and we want to show that W can be the resultant when I multiply U by a scalar and V by a scalar. So I got my ruler here, and you might have to be a little bit patient with me as I get used to this smartboard ruler. Here we go. Okay, not bad. So I know that W has to be the result. So I know I'm going to have some scalar multiple of U that, and it's, I can see the scalar is going to be negative, by the way. Trying to do a dotted line, I suppose I could have, there, that's not too bad. And I don't know how long it is. That's why I'm making it longer than I need to. Um, and then, and this is going to be like K times U. And I know K will be negative. All right. So what about V? Well, now I got to grab my ruler. If I can grab my ruler here, grab my ruler right by the, okay. And then I need a copy of V, right? And I'm just trying to make it parallel. This should be easy for you to do. That's not awesome. That's not awesome. I might have to do, oh, wait, there we go. There, that's a little bit better. So there's now my vector V is parallel. And I know that I got to copy this so that the resultant is W. It's almost like I'm trying to make my triangle or my parallelogram. And in fact, there I go. This is going to be the scalar multiple of V. And I know this is the scalar multiple of V because it's parallel, right? And so if I draw some arrows on here, now this is going to be, this thing here is K times U. And this vector, this little tiny vector here is L times V. And I know KU plus LV is equal to W, where W is any old vector. And notice that if you like the parallelogram rule better, well, then I could also make my parallelogram because I grab a copy of U, or KU actually, and I'm going to put it over here. I'm going to make it blue so it's all nice, it looks nice. Get rid of U. Go on, get rid of U. And then I got my dotted there. And then I've got, this is LV, right? And so now back on my note, I've found my values of K and L so that a linear combination of this is any old vector in the plane. Notice my ability to do this means that U and V are a spanning set for R2. That means any old vector in the plane can be written as a linear combination of those two. So that means U and V are a spanning set. Another way to say this is U and V are a basis for their plane. The idea of the information stored in vector U and vector V are enough to give me any vector in their plane, which is pretty cool. Another terminology, and all of these things, the old ones in green and the new ones in red, are all equivalent. U and V are said to be linearly independent. Linearly independent. A basis for their plane, a spanning set in their plane. Any vector is a linear combination of the two given non-collinear vectors. All of these mean the same thing. In contrast, then, what are these then? Well, these are not, and this, you can add this to your page 2, not a spanning set. They're not a basis. And they're not, we can say they're not linearly independent, but use some English knowledge there. They're actually linearly dependent. Dependent. Linearly dependent. Okay. Are you ready to go to 3 dimensions? Me neither, not yet. I'm going to stop and do another little short video in a moment.